Hi viewers, welcome to all. Here we are discussing about a project recurrent neural network with column-wise matrix vector multiplications on FPGA. This article presents a reconfigurable accelerator for recurrent neural network with a fine-grained column-wise matrix vector multiplications. We propose a novel latency-hiding architecture for recurrent neural network accelerations using the column-wise matrix vector multiplications instead of state-of-art row-wise multiplication operations. The hardware architectures can eliminate the data dependencies to improve the throughput of the RNN interference systems. Besides, we introduce a reconfigurable checkerboard tailing strategy with allow the large weight matrix. So while incorporating various configurations of the element-based parallelisms and vector-based parallelisms. Okay, proposed work of this paper was designed the row-wise matrix vector multiplications and column-wise matrix vector multiplications using LSTM vector method. Okay, and the row-wise matrix vector multiplications implemented with a row bypass multiplier and column-wise matrix vector multiplications implemented with a column bypass multiplier. The row and column vector multiplications using a sliding functions at 8 cross 8 matrix sizes. Okay, so in the end, this work was proposed and developed in Verla HCL and synthesized in Xilinx Vertex 5 FPGA and compared all the parameters in terms of area, delay and power. Okay, now we can verify the base paper. This is a base paper title and abstract. This base paper is fully designed for to mainly focus for the column wise matrix vector multiplications, and the existing system of this paper is a row wise matrix vector multiplications. To overcome the row wise multiplications, this column wise matrix vector multiplications as a proposed work of this paper. Okay, so what we have done in the paper means we are implemented both the work row wise matrix vector multiplications and column wise matrix vector multiplications. Okay, for the multiplication process we are used the two reference papers on here. Okay, so one is the design and low complexity implementations of matrix vector multiplier for iterative method in communication systems. Okay, this is also matrix vector multiplication. Here they are used some sliding method and selector method. Okay, so we are used this sliding methods and selector method in our paper. Okay, so this is a sliding function method to multiply the matrix. Okay, that means here we are used as a 8 cross 8 matrix and a 1 cross 8 matrix. Okay, so we need to multiply the row into column and column into row means, okay, we have used this sliding functions. It will be create a more architecture reductions and low cost in this paper. Okay, and this is another one paper. This is again our reliable multiplier designs with adaptive hold logic. We are used the two multiplier functions here. Okay, here the figure 2 shows the 4 cross 4 column bypass multiplier and the figure 3 shows a 4 cross 4 row bypass multiplier. This two multipliers we are used in our work. Okay, but we have designed a 8 cross 8 row bypass and 8 cross 8 column bypass multiplier. We are not used 4 cross 4. We have designed this work in 8-bit only. Okay, and this is a architecture of this paper. This is a basic one, row matrix vector multiplications and column wise matrix vector multiplications. Okay, and this is a proposed thing they have shown in the figure 4. Okay, so row wise and column wise matrix vector multiplications with the LSTM based data dependency analysis. Okay, now we can show the coding part. Okay, so this is a coding for the column wise matrix vector multiplications. So here we are used column wise matrix vector multiplications means we have used 8 into 8 matrix. Okay, so each matrix one single bit equal to 8 bit sizes. Okay, that means 8 into 8 equal to 64 into 8 means we have used a 512 bit. Okay, so here we are given as a 512, 511 down to 0 is the input, and 8 into 1 means 8 into 8 64, right? So the another input is a matrix input is 1 cross 8 equal to 63 down to 0, so 64 bit. Okay, so this 512 bit we have given the input on here. Okay, here this is a data input 2 and this is a data input 1. This data input 2 will be incremented on every 10 signal. So if you need increment on data input 1 also, we can change the input. Okay, and here we are given all the inputs equal to 1. For verification purpose we are used this one. Okay, if you need some other value you can change the value on here. Okay, so this is all the data input 1 part. Okay, so here this is the first row, and second row, third row, fourth row, okay, up to 8 we have filled the values, okay. And this is the top model of the code, the column wise matrix vector multiplications, okay. So here we are used as a input clock reset and input matrix input 8 cross 8 and matrix input 1 cross 8, and this is all the output data 1 to data 8, okay. So first, the initial case, this is a LSTM controller. So this controller will control the data, so when it will be add and when which bit we need to add, okay. So the adding functions and the selection functions, okay, this kind of things it will be controlled, okay. So that is a LSTM configure as per the base paper. This is a sliding function. So based upon this paper sliding functions, we have used the value, we are given the input, and we are taken the output, okay. So that functionalities will be happen on here. So here we are given the input, okay, that means dx1 to dx8 and dy1 to dy8. So we are multiplied the values on here, and we are taken the multiplications value, data register 1 2 3 4 5 6 7 8, okay. So this 8 values we have added in vector addition, okay. So that addition part we have used in the LSTM controller, okay. So this is the functionality of this column wise matrix vector multiplications, okay. So instead of this sliding functions, we have used as a column bypass multiplications, and the row multiplication also we have used, okay. This is a row wise multiplications, okay. And here the selections methods of the matrix of sliding functions, it will be differed, okay. So here 7 down to 0, 71 down to 64, but in the column wise multiplications we have used 7 down to 0, 15 down to 8, okay. So based upon the switching activity of the matrix, okay, we have given this value, okay. This is a simulation for column wise multiplications, okay. So here we are given an input, 5 total input and 64 input, okay. So here these are the outputs, okay, 16 24 32 48 40 56 64, okay. And this is the next cycle. So once done came, the value will be incremented in the test bench, okay. So based upon the value, input value, we will multiply it and we will provide the output on here, okay. And you can check the sub models, okay, LSTM controller, vector additions, okay, sliding functions, okay. And this is a row multiplications, row wise multiplication. So here row wise multiplications also we will get a same output only, because the method of row and column wise multiplications, it will be different, but the output will be same, okay. That is a main thing on here, okay. So here we are checked it. So here 16 24 32 40 48 56 64, okay, all the outputs will be same, okay. And we have synthesized this code in Xilinx Vertex 5 FPGA. So this is a column wise matrix vector multiplication. Here you can check the comparisons. So number of slice registers, LUTs and occupied sizes, IO base, okay. And you can check the RTL schematic, okay. This is a column wise matrix vector multiplication. So here we are given the input, okay. So this input directly given to the sliding functions, okay. Sliding functions, we are used 8 sliding functions on here, okay. So for novelty based architecture, we are used this 8 sliding functions, and inside of this sliding functions we have used as a column bypass multiplications, okay. So this is a column bypass multiplication code, okay. So this is a column bypass partial product generation, okay. And so after this sliding functions, all the data output we have added in the vector additions. So this vector additions we have used as a ripple carry addition, 16-bit ripple carry addition method, okay. So this is the architecture for 16-bit ripple carry addition method. And after this vector additions, we are given this output to LSTM controller, okay. And you can check the delay value on here, okay. Delay value equal to 112.416 nanoseconds, okay. And the row wise multiplications, so these are the values, number of slice registers, number of LUTs, number of occupied slices, number of IO base, okay. And delay, you can check here, delay value equal to 112.416 nanoseconds. And you can check the row wise matrix multiplications, okay. So here the architecture, overall architecture will be same only, but inside of this architecture, we have changed the input sequence, the 15 down to 0, 7 down to 0, right? Okay, that sequence we have changed it, and inside of this sliding functions we have used as a row bypass multiplication. These are the vector additions and the LSTM controller for row wise matrix multiplication. And this comparisons we are updated in the comparison document. This is a comparisons for row bypass and column bypass multiplication. These are the comparisons values. Okay, and here you can check the overall top comparisons, okay, for row wise matrix multiplications and column wise matrix multiplication. Okay, here you can check all the values. And we are written an abstract document for this project. So this is a base paper abstract, improvement of the project, proposed title, proposed abstract, existing system, and disadvantages, proposed system. Okay, so advantages, related notes. Okay, and finally literature survey and references. Okay, we have updated all the things. Okay, that's it. Thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.